Alright, so in this video I'm going to go over Gibbs free energy a little bit more, and you will be asked to predict whether a reaction is going to be spontaneous or non-spontaneous based on just not even knowing the values of the enthalpy and the entropy, but just knowing whether it's positive or negative. So you do need to know this. Now you can memorize it if you want, or you can just simply reason your way through it. So what I like to do is I like to say, okay, if I have delta H is my enthalpy. If you have a reaction that's exothermic, that means you're releasing energy. So if you're releasing energy, products have less potential energy, which makes them more stable. So if it's negative, that usually is favorable. But remember, whether a reaction is going to be spontaneous or not is not going to deal with just enthalpy. It's also going to be up to the entropy. So in chemistry, the universe is always increasing its disorder. So whenever we have a reaction that creates more disorder, that is favorable. So when delta S, remember S is for entropy, which is disorder. When it's positive, that is favorable. So if delta H, enthalpy, is negative and delta S is positive, then that's two favorable things. So if that happens, which it does in this scenario, delta G will always be negative, which means that it's spontaneous. So if delta G is negative, then you have a spontaneous reaction. So if we look at this scenario right here, well, delta H is positive, which means it's endothermic, which means it requires energy. So that's not usually favorable. And then also entropy is negative, which means I just created more order. Well, if that's the case, then this reaction is not going to be spontaneous because I have two non-favorable items. So let's look at a few other situations. All right, so delta H. If delta H is positive, which means it's endothermic, that's not favorable. But if delta S is positive, that is favorable because I'm creating more disorder. So I've got one thing that's favorable and one thing that's not. So at the end, it will be up to the temperature as to whether this reaction is going to be spontaneous or non-spontaneous. So what I do is I look at delta H. Well, delta H is positive here, which means it's endothermic. So if it's endothermic, it requires energy. It requires more energy because you're going to put energy into the system. So if it requires energy, temperature is one way to give it energy. So if you have a high temperature, then the reaction is probably going to happen. So it will be spontaneous at a high temperature because it's endothermic. Well, at a low temperature, you're probably not going to get enough energy to make the reaction happen. So in this case, delta G would be positive or non-spontaneous if it's a low temperature. The last situation is where both delta S and delta H are negative. Well, if we have a negative delta H, that means that it's exothermic, which means that it will release energy, and this is favorable. Well, if we have negative entropy, that means I'm increasing my order or decreasing my disorder. So that's not favorable. So we have one that's favorable, one that's not, so then that means it's going to depend on the temperature. So in an exothermic reaction, we release energy. So that means that I have this reaction maybe. CO2 plus water. Well, if it's exothermic, that means that energy should be a product. Well, if energy is a product, then I probably don't want it to be a high temperature because that means that I've got more energy, and if I put energy into it, usually the reaction is if we're going with Le Chatelier's principle, will shift in the opposite direction and actually start making reactants again. So if it's an exothermic reaction, we like it to be at a low temperature because I'm going to release that energy as a product. If it's a high temperature, then I've already got energy as a product, and I've got energy in the atmosphere that's not favorable. So in this situation where they're both negative, it will be spontaneous at a low temperature and then non-spontaneous at a high temperature. All right, so this is an example of a question you might be asked. So the entropy and the enthalpy of a reaction are both negative. Is the reaction spontaneous? So again, you can just memorize it if you want. I don't recommend that because chances are you'll remember it for the test. You might remember it for the test, but then you might not remember it in a month. So I will reason my way through this. So delta H is negative, and delta S is also negative. So if I have a negative delta H, that means it's exothermic, which is favorable. And then if I have a delta S that's negative, that means that I am increasing my order, or I can say decreasing my disorder. So if I'm increasing order, that's not favorable. So I have the situation where I have one thing that's favorable and one thing that's not. It will depend on the temperature. So that means if I look at delta H, it's exothermic. Well, in an exothermic reaction, I'm going to release energy. So I would want the surroundings to already be at a low temperature. So delta G will be negative if we have a low temperature. And that means that it will be spontaneous at a low temperature. If it's at a high temperature, the reaction is not going to be spontaneous. And then you can also look at your equation for Gibbs free energy, and then that might help you too. So I know that I have a negative number for delta H. I also know that I have a negative number for S. So in order for this reaction to also be, for this to be negative, for delta G to be negative, this number, this temperature has to be low enough so that we don't create a positive number for delta G. All right, so suppose that a reaction has delta H of this and S of this. What temperature will it go from spontaneous to non-spontaneous? Well, remember when delta G is negative, then it's spontaneous. And when delta G is positive, it's non-spontaneous. So that means that if we are going to switch from being spontaneous to non-spontaneous, well, at 0, that's when that threshold happens. So we're going to say that delta G here is going to be 0. Because 1 degree higher, 1 degree lower, you're going to switch the sign of delta G. Either bring it positive or bring it negative. So delta G is equal to this. We are looking for a temperature in this case. So delta G, we're going to say is 0. Delta H is negative 28 kilojoules. So we have delta H in kilojoules and delta S in joules. So we're going to switch one of them. So let's just switch the delta S. Minus temperature, which we don't know, and it's not going to be negative 60. We're going to switch it to kilojoules, so it's going to be negative 0.06. All right, so let's add out the 28. So 28 is equal to negative T times negative 0.06. Well, negative times a negative will just give me a positive. All right, so divide both sides by 0.06. And when I do that, I get 466.66, so 67, and that's going to be in Kelvin. So at this temperature, if I were to go, so this is going to be the temperature at which delta G is negative, so that means that if I go 1 degree higher, 1 degree lower, it switches from being positive to negative here. All right, so if a reaction has a positive value for enthalpy and a negative value for its entropy, which of the following is true? Okay, so again, I'm going to analyze it. Okay, so delta H is positive here, and delta S is negative. All right, so I know that for this, this is an endothermic reaction, which is not favorable. And if delta S is negative, then that means that I am creating more order, which is also not favorable. So that means that I've got two components that are not favorable. Delta G will not be spontaneous, so it will be positive. Okay, so with our choices, if delta G is positive, it is non-spontaneous here. All right, so there's another way to calculate delta G, and it's the same way that you can calculate delta H and delta S. If you're given the products and the reactants, the free energy for both of those, then you can simply do products minus reactants, and this little f is for formation. And also, if you see a little symbol that looks like this, and unfortunately it should be a superscript here, that means that we're set at standard conditions. So if we have standard conditions for thermochemistry, that means the temperature is equal to 298 Kelvin. Not 273, but 298. All right, so let's look at an example. Okay, so calculate the free energy change for the combustion of 1 mole of methane. Is this reaction spontaneous? Okay, so first thing, we need the reaction. So we have methane. If it combusts, that means that I'm burning it in oxygen gas. I'm producing CO2 and water. Anytime that you burn a hydrocarbon, you're going to make CO2 and water. All right, so I need to balance it. So I have 2 oxygens. Okay, so 2 here. All right, so now what we're going to do, we're going to do products minus reactants, and we're also going to make sure we account for the coefficients. So our first product would be CO2. We've got 1 of those. So 394 times 1. So I'm doing my products first, plus my water. I've got 2 moles of that. All right, so those are our products minus our reactants. Well, we have CH4. We've got 1 mole of that, so that's negative 50.8 times 1. And then plus the O2. Well, they don't give you O2, and that's because O2 is in its standard state. So right here, well, they don't actually say that, but right here, if you have O2, if you have a situation like this where they don't give you an enthalpy or a Gibbs free energy or an entropy, it's probably because they expect you to know that it's supposed to be 0. So it's O2, it's in its standard state, so it should be 0. So really we don't even need to write it in there. All right, so we do the math here. Okay, so you get negative 868 here. And then here you'll get negative 50.8. So minus negative 50.8. You're going to get a delta G of negative 817.2. And, oh, units were not given here, but it's probably going to be in kilojoules per mole. All right, so sometimes we have reactions that are actually non-spontaneous. Well, how do we get those reactions to actually happen? Well, if delta G is positive and it's non-spontaneous, you can apply energy to the reaction. You can do this a couple different ways. You can apply electricity. So like if I take water and I'm trying to split it, this is definitely not a favorable reaction. I could add electricity to the water and actually split it into the H2 and O2. I could also add another energy source like light, or I could couple an unfavorable reaction with a favorable one, and this happens in your body all the time. So photosynthesis is a reaction in which I make C6H12O6, so glucose, which is a high energy product. So normally this would be a very non-spontaneous reaction, but it's photosynthesis. We add light energy to it to make it happen. So even though delta G is positive, the reaction will still happen because we can force it to happen by adding more energy. Now, coupling is something that happens in the body all the time. So in the process of breaking down glucose, you actually have to add a phosphate group to it. So that's one of the first steps in actually breaking down the glucose. This is a positive delta G, which means that it is non-spontaneous. Well, I take ATP and I break it, so I make ADP and then I take off a phosphate group. That is a negative reaction. So this is spontaneous. But in order to break down the glucose, this reaction has to be coupled with the putting the phosphate on the glucose. So even though the first reaction is not spontaneous, the second reaction is spontaneous, and the magnitude is high enough to make the reaction overall work and make it be spontaneous. All right, so when we talk about equilibrium, or when we talk about Gibbs free energy, we need to talk about equilibrium too. So delta G free energy is equal to negative R times the temperature times ln of K. So this right here, this is the gas law constant. And this is on your reference sheet. So you're going to use this one though, because it's got joules in it, and we're dealing with energy. So you're going to use the one that includes the unit of joules. So you're going to keep your temperature in Kelvin, and then you take the natural log of K. Well, if you have a large negative G value, remember that's spontaneous, that will indicate that I'm going to make a lot of products because it's a favorable reaction, it's spontaneous, which means if I have a large negative G, I'm going to have a large positive K. So K is going to be greater than 1. I'm going to make a lot of products. It's a favorable reaction. So if delta G is positive, then that means that K will be less than 0. And then if it happens to be equal to 0, delta G is equal to 0, then that means that I'm going to make an equal amount, or I'm sorry, the forward rate and the reverse rate will be equal to each other. All right, so when we talk about Gibbs free energy, if we have, and this actually applies to delta H and delta S. If you have this little symbol right here, that means that we have set conditions. The normal conditions will be 1 atmosphere pressure. If it's a solution, it's 1 mole per liter. Also, temperature is equal to 298 Kelvin. That's important for you to remember. So if you change any of these variables, you're going to change what G is. And you will not be required to do any kind of calculations with this. But basically what you need to know is if you change any of these conditions, you're shifting the equilibrium. So you're going to change Q. So remember, when we're at equilibrium, Q is equal to K. But if you change anything, if you add a product, add a reactant, take one out, if you change the temperature, then they're no longer equal. And then that's going to change what your delta G is. All right, so let's look at something like this. Okay, so if the reaction quotient is greater than the equilibrium constant, what's true of Gibbs free energy? Okay, so what we have to think about is we have to think about where the reaction is shifting. And it says Q is greater than K. Well, when we think about Q and also K, we have products over our reactants to the power of their coefficient. Well, if Q is too big, that means that this number is too big. So if Q is greater than K, then that means Q is too big. So what I like to think about is if Q is too big, then that means the products are too high. So I need to get rid of the products and go to the reactant side. So this reaction will shift to the reactant side. Okay, so you can think about it like this. If Q is greater than K, then that means that Q is too big. Well, then that means the product number is too large. We need to get rid of some of the products and go to the reactant side. Or you can think about it like this. If you have Q and it's too big, that means the reactants are too small. So we need to go shift to the side and make more reactants. So that means that if we're going to the reactant side, the reaction's no longer favorable because we're not making lots of products. So delta G will be positive. So that means that it is greater than 0 here. Now let's say that the opposite were true. If Q was less than K. Well, if Q is less than K, then that means that this number is too small. So if this number is too small, then that means that the reactants are too large. This bottom number is going to be too large. So that means I need to shift to the other side and make more products to get rid of the reactants. So if Q is less than K, then that means we're going to shift to the product side, which means that delta G will be negative. It's spontaneous at that point. I think that's it for this one. All right.